If the idea of two solar storms merging into a single amplified shockwave aimed directly at our planet got you locked in right now, take a second and hit subscribe to Orbital View. We're tracking this event in real time, from the moment the first ejection left the sun through the full geomagnetic aftermath, and we'll be here when the data comes in. Drop a comment below with this. How many hours of battery backup does your home actually have if the grid goes dark right now? I read every single one. Here's what we're getting into. The physics of why two storms merging is exponentially more dangerous than either one arriving alone. The history of the one event in the modern era that came closest to shutting down civilization, and what it cost. And the single structural vulnerability in the North American grid that space weather engineers have been warning about for 20 years, which is sitting directly in the path of what's coming. Let's get into it.
There are two clouds of magnetized plasma moving through space at this moment, and they are aimed at you. The first left the sun approximately 40 hours ago. Solar observatories, specifically the Solar and Heliospheric Observatory, the spacecraft the international community calls SOHO, positioned roughly 1,000,000 miles from Earth between our planet and the sun, captured the eruption. The Solar Dynamics Observatory, SDO, in low Earth orbit, imaged the source region in extreme ultraviolet light with its atmospheric imaging assembly. What those instruments showed was a full hollow coronal mass ejection, a CME so large and so directly Earth-directed that it appeared in coronagraph imagery as a ring expanding outward from the solar disk in every direction simultaneously. Full halo events are not common. When forecasters at the NOAA Space Weather Prediction Center in Boulder, Colorado, see a full halo signature in LASCO coronagraph data, there is no ambiguity about the trajectory. It's coming here. The first CME is moving at roughly 800 kilometers per second. That is fast by almost any measure, nearly 0.1% of the speed of light. But in the context of what is following behind it, that speed is almost incidental. Because the second ejection, launched from the same active region on the solar surface within hours of the first, is moving at more than 1,800 kilometers per second. Let me give you a physical sense of what that means. The average distance from the sun to Earth is approximately 150 million kilometers. We call it 1 astronomical unit. The first cloud left the sun and has been crossing that distance for the better part of 2 days. The second cloud is crossing the same distance in less than 24 hours. The gap between them has been closing the entire time, and the math is not subtle about what happens next. At the current differential in speed, the second ejection catches the first somewhere between the orbit of Venus and the orbit of Earth. The exact intercept point depends on precise measurements of each cloud's velocity profile. CMEs decelerate as they plow through the solar wind, and the first cloud has been sweeping the interplanetary medium clean ahead of it, which actually makes the second cloud's transit somewhat faster by reducing drag. Forecasters at the Space Weather Prediction Center have been running ensemble models, cross-referencing data from the Stereo A spacecraft, positioned off to the side of the Earth-Sun line, and the output is consistent enough to worry about. The merger is happening, and it is happening on the approach. The merged structure will arrive at Earth's magnetosphere, the magnetic bubble that surrounds our planet and deflects the solar wind, within a window of 48 to 72 hours from the first ejection's launch. The Deep Space Climate Observatory, DSCOVR, positioned at the L1 Lagrange point roughly 1,000,000 miles sunward of Earth, will be the first instrument to register the shockwave. When DSCOVR's magnetometer and plasma sensors see the arrival, forecasters in Boulder will have approximately 15 to 60 minutes to update warnings. 15 minutes if the impact is fast, 60 if it's slower than modeled. What they are warning about right now before the impact is severe geomagnetic storming. The official NOAA G-scale runs from G1, minor, barely noticeable, to G5, which is the top of the scale. G5 is described in NOAA's official documentation as an extreme event associated with widespread voltage control problems, protection system false tripping. Some grid systems may experience complete collapse. The documentation also notes surface charging of spacecraft, complete blackout of HF radio communications, and that the aurora borealis may be visible as far south as Florida and Texas. These are not projections from the most alarming corner of the internet. These are the official benchmarks from the agency that operates the National Warning System. And here's what I want you to sit with for the next 2 hours of this investigation. The storm heading toward Earth right now has the physical characteristics to push well beyond G5 levels. The G-scale tops out at 5, not because the physics stops there, but because the scale was calibrated against the historical record, and the historical record does not include many events like what is coming. The scale has a ceiling, the event may not respect it. The reason this particular merger is so dangerous comes down to one measurement that most of the coverage will never mention. Forecasters don't just care about the speed of the incoming plasma or the density of the magnetic field. The single most operationally critical parameter, the one that determines whether a geomagnetic storm is an inconvenience or a catastrophe, is the orientation of the magnetic field embedded inside the CME. Specifically, whether that field is pointing south. Magnetic fields have direction. The Earth's magnetic field at the poles points roughly northward into the planet. When a solar storm arrives with a magnetic field also pointing northward, the two fields are aligned, and the magnetosphere, like two magnets with matching poles facing each other, pushes back. The storm's energy is deflected. The interaction is relatively mild. But when the CME's embedded magnetic field is pointing south, when the polarity is what physicists call southward BZ or negative BZ, the two fields are antiparallel. They reconnect. The magnetosphere essentially opens a door, and the energy of the solar storm pours through. The critical phrase in every space weather forecast right now is sustained southward BZ. A large, fast CME with southward BZ that persists for hours is the recipe. And the structure of a cannibal CME, the specific kind of event unfolding right now, compresses and amplifies the magnetic complexity of both original ejections into a single, denser structure. The trailing faster cloud overtakes the leading slower cloud and crushes it from behind. The two magnetic field structures, the two plasma sheaths, the two shock fronts, collapse together into one wall of magnetized plasma with a combined magnetic field far stronger than either ejection carried alone. I have spent the last several days reading the Space Weather Prediction Center's forecast discussions, the European Space Agency's Space Weather Service bulletins, and the output from the Enlil Solar Wind Propagation Model. The primary numerical tool NOAA uses to forecast CME arrivals. The model is showing something that the forecasters I've read are describing carefully. The way scientists describe things when they are trying not to alarm, but also trying not to paper over what the data says. The word they keep coming back to is amplified. The merged structure is amplified. The southward field component is amplified. The impact velocity when the merged cloud strikes the bow shock of Earth's magnetosphere will be amplified beyond what either individual storm would have delivered. This is not a normal solar storm warning. This is the specific combination of factors that has historically, when it has occurred, caused power outages, satellite losses, and communication disruptions on a scale most people today have never experienced. And we are going to spend this investigation understanding exactly why. Not to frighten you, but because the physics is genuinely remarkable, and because you deserve to understand what is actually happening above your head right now. Picture the sun the way most people picture it, a glowing ball, burning steadily, warming the Earth from a safe and comfortable distance. That picture is wrong in almost every way that matters for this story. The sun is not a ball of fire. It is a ball of plasma, a fourth state of matter so hot that atoms themselves break apart, electrons stripped from their nuclei, protons and electrons moving independently in a charged soup. The surface temperature, a term that already requires qualification because the sun has no solid surface, is approximately 5,500 degrees Celsius. But the outer atmosphere, the corona, the tenuous glow visible only during a solar eclipse, is inexplicably millions of degrees hotter. Physicists have been working on explaining this for decades. The corona is hotter than what's below it, which violates the intuition that things should cool as you move away from the heat source. The leading explanation involves magnetic waves, Alfvén waves, carrying energy from below the surface and depositing it in the corona. The mechanism is still being refined. The temperature differential is not in dispute. And that corona, that unimaginably hot outer atmosphere, is threaded through with magnetic field lines that emerge from the solar surface and loop back into it like enormous invisible arches spanning thousands of kilometers. These loops are not stable. The sun rotates differentially, the equator spins faster than the poles, and over the course of the 11-year solar cycle, this differential rotation twists, braids, and tangles the magnetic field lines until they carry enough stress to snap. When a bundle of magnetic field lines snaps, it releases energy. The snap can launch a billion-ton cloud of plasma off the solar surface at millions of kilometers per hour. That is a coronal mass ejection. And the comparison I keep coming back to is this. Imagine taking a rubber band, stretching it until it breaks, and watching the energy release fling an object across the room. Now scale that rubber band up to the size of a continent, charge the rubber band with the electromagnetic energy of 1,000 nuclear weapons, and fling an object the size of a small planet. That is roughly the physics of what just left the solar surface. The plasma cloud that a CME launches doesn't just travel through empty space. It travels through the solar wind, a constant stream of charged particles flowing outward from the sun in all directions, filling the entire inner solar system. The CME plows through this solar wind like a boat through water, creating a bow shock at its leading edge. The shock compresses and heats the solar wind ahead of it. Behind the shock is a sheath region, turbulent, compressed plasma dragged along by the ejection. And at the core of the structure is the magnetic flux rope, the coiled, tangled magnetic field that was originally embedded in the corona before the eruption, now carrying its polarity signature across space. It is this flux rope, specifically its southward pointing or northward pointing orientation, that determines what happens when it reaches Earth. The flux rope is the loaded gun. The speed and density are the gunpowder. The orientation of the bullet determines whether the magnetic door opens. Now here's what happens when two of these structures collide in transit. The faster CME has a higher ram pressure. It is pushing through the interplanetary medium with more force. When it catches the slower ejection ahead of it, the leading edge of the second cloud slams into the trailing edge of the first. The interaction is not a clean merger. It is a collision, and what emerges is the structure the community has taken to calling a cannibal CME, the second ejection literally consuming the first. The consumption process does several things simultaneously. It compresses the plasma of both clouds into a denser sheath. It amplifies the magnetic field's strength. Two sets of compressed field lines occupying less volume means a stronger combined field. And critically, it can alter the orientation of both flux ropes. The collision introduces turbulence at the boundary between the two structures. The magnetic field orientation in the merged sheath region becomes harder to predict and can rotate during transit, sometimes arriving at Earth pointing in a different direction than forecasters projected at the time of the initial eruption. This last point is the honest scientific uncertainty at the center of this entire event, and I want to name it clearly because this channel does not paper over uncertainty. The models are good, the physical reasoning is sound, but the exact southward BZ value that this merged structure will deliver when it arrives at Discover will not be known until the instrument sees it, approximately 1 hour before the storm hits. That is the forecast window for the single most operationally critical parameter in the entire event. 1 hour. Power grid operators across North America, Europe, and Asia, those who are paying attention, which is not all of them, are watching this window with very little ability to act in it. Shutting down a major high-voltage transmission network in an orderly way takes more than 1 hour. The grid is not built for the speed of space weather. Let me tell you what that means in practice. And to do that, I need to go back to the last time something like this came close to happening, and how close it was to changing everything. The year was 1859. The month was September. A British amateur astronomer named Richard Carrington was at his telescope in Redhill, Surrey, sketching sunspot positions as part of a routine observational program. At approximately 11:15 in the morning, local time, he saw something no astronomer had ever recorded: a sudden, intense brightening over a cluster of sunspots. Two kidney-shaped patches of white light appeared near the edge of the sunspot group and moved across the solar surface over the course of approximately 5 minutes before fading. Carrington made a precise sketch and immediately sent word to the Royal Astronomical Society. He also noted the time precisely. He did not yet know what he had seen. What he had seen was the optical signature of the largest solar flare in the recorded observational record. The X-ray and ultraviolet surge of energy from a magnetic reconnection event so powerful that it was visible to the naked eye as white light against the already blinding solar disk. This was remarkable in itself. But it was what followed 17 hours later that embedded September 1st and 2nd, 1859, in the history of extreme events. The coronal mass ejection launched by that flare arrived at Earth in approximately 17.5 hours. Normal transit time for a CME is 1 to 3 days. This one traveled the same distance in 17.5 hours, implying an ejection velocity of roughly 3,000 kilometers per second, well over 4 times the velocity of the faster of the two storms now approaching Earth. The solar wind ahead of it had been partially cleared by an earlier ejection, reducing drag. The path was partly swept. And the merged structure, because there likely was a preceding CME interacting with this one, making Carrington itself arguably a cannibal event, hit Earth's magnetosphere like nothing the planet had experienced in the modern era of telegraph communication. The aurora was visible in Cuba, in Rome, in Hawaii, and in Queensland, Australia. Rocky Mountain gold miners woke up in the middle of the night believing it was dawn from the brightness in the sky over their encampment. Telegraph systems across North America and Europe, the entire global communications infrastructure of the era, failed simultaneously. But they didn't just fail. They caught fire. Telegraph operators reported being shocked by their equipment. Paper and telegraph offices caught flame from sparks arcing across the apparatus. Some systems, disconnected from their power sources entirely, continued to transmit messages because the geomagnetically induced current in the telegraph wires was so strong it powered the equipment on its own. Geomagnetically induced current, GIC. This is the mechanism that connects space weather to power grid failure, and it is the mechanism that makes cannibal CME events so specifically dangerous to modern civilization. I need you to understand this because the coverage rarely gets this specific, and without it, the scale of what could happen over the next 48 hours is impossible to appreciate. When a severe geomagnetic storm compresses and distorts the Earth's magnetic field, it is not a static disturbance. The magnetic field is moving. It is changing, oscillating, sweeping across the surface of the Earth over the course of hours. And by Faraday's law of electromagnetic induction, a changing magnetic field induces an electric current in any conducting material caught inside it. The Earth's crust is a conductor. Long metallic structures on or near the surface of the Earth, pipelines, telegraph wires, railroad tracks, and most critically high-voltage electrical transmission lines, act as antennae for these induced currents. In 1859, the conducting structures on Earth were mostly short. Telegraph lines, yes, but nothing like the modern grid. Today's high-voltage transmission lines span thousands of kilometers. They are, for GC purposes, enormous antennas, perfectly sized to couple with the slowly oscillating magnetic field disturbances that a severe geomagnetic storm produces. The induced currents flow into the power grid, into the transformers that step voltage up and down at substations, and into the core of those transformers they do something catastrophic. Transformers work on alternating current, AC power that reverses direction 60 times per second in North America, 50 times per second in most of Europe. They are designed with exquisite precision for this operating frequency. The geomagnetically induced currents are not alternating. They are quasi-DC, they flow in one direction, and they do not reverse. When a quasi-DC current flows into an AC transformer, it drives the transformer into what engineers call half-cycle saturation. The transformer's iron core saturates magnetically on one half of every AC cycle, drawing enormous reactive current, generating massive amounts of heat, and producing harmonic distortions in the power waveform that can cascade across the grid and trigger protection systems designed to isolate faults. Those protection systems, doing exactly what they were designed to do, begin disconnecting portions of the grid, one after another, in sequence, or in a worst-case scenario, simultaneously across a wide geographic area. The Carrington Event, by the best estimates physicists have made by measuring the signature it left in ice cores from Greenland and Antarctica, where the charged particle influx deposited nitrate compounds preserved in annual ice layers, was roughly twice as intense as the most severe storm of the 20th century. Twice. The storm that defines the modern high water mark was the one that knocked out the Hydro-Quebec grid in March of 1989, leaving 6 million Canadians without power for approximately 9 hours. Carrington was more than twice that. And Carrington-level storms, based on the ice core record, occur on timescales of once every 100 to 150 years. The last one was 165 years ago. The storm approaching Earth right now is not a Carrington event. I want to be precise about that because precision matters here, and overclaiming damages the credibility of an investigation. The events are not equivalent, but the physical mechanism, cannibal CME, amplified magnetic field, compressed sheath, uncertain southward BZ, is the same type of mechanism that generated the events in the historical record that forecasters point to when they are asked what the upper bound looks like. And the upper bound is not academic anymore. It is operational. It is arriving. March 13, 1989. This is the case study that every power grid engineer and every space weather forecaster knows. It is the calibration event, the closest modern analog to what happens when a severe geomagnetic storm makes contact with a large interconnected electrical grid. And the details of that night are worth spending time on because they are not well known outside the engineering community, and they are directly relevant to the next 48 hours. The storm was triggered by a large solar flare on March 10. The CME arrived at Earth 3 days later, early on March 13. The KP index, the Planetary Geomagnetic Activity Index that runs from 0 to 9, with 9 being the most extreme, hit 9, pegged at the maximum, before 5 o'clock in the morning. At 2:44 in the morning, the first event occurred. The Legrand network in northern Quebec, operated by Hydro-Quebec, began experiencing voltage instability. Protective relays at the Chibougamau substation tripped, then another relay, then another. At 2:45:73 seconds after the first relay tripped, the entire Hydro-Quebec grid lost synchronization and collapsed. 6 million people lost power in approximately 90 seconds. The collapse was not caused by physical damage to the lines or the poles. It was caused by the protection systems doing exactly what they were supposed to do: detecting voltage anomalies and disconnecting the affected equipment to prevent damage from spreading. The problem is that in a geomagnetically induced current event, the anomalies are everywhere simultaneously. The protection systems, responding to a grid-wide disturbance rather than a local fault, isolated piece after piece until there was nothing left connected. The restoration took 9 hours. 9 hours is not a catastrophic outage duration in the context of industrial civilization. Uncomfortable, disruptive, commercially costly, but not civilization threatening. The reason the 1989 event was not catastrophic is specific, and this specificity is important. The surge of GIC through the Hydro-Quebec system was not strong enough or sustained enough to thermally damage the large power transformers at the core of the substations. The transformers experienced half-cycle saturation, produced harmonics, triggered protective relays, but they survived. They could be reconnected. Power could be restored. The nightmare scenario, the one that the Federal Energy Regulatory Commission, FERC, the North American Electric Reliability Corporation, NERC, and a small community of space weather engineers have been trying to communicate to policymakers for more than a decade, is an event strong enough and sustained enough to thermally damage large power transformers. Because large power transformers are not like circuit breakers or fuses. You do not replace them in hours or days. Large high-voltage transformers, the ones that step power up to 765,000 volts for long-distance transmission, are custom-built, cost between $3 and $10 million each, weigh up to 400 tons, and cannot be moved by ordinary transportation. The global manufacturing base for these transformers is concentrated in a small number of facilities. Lead time for a new transformer in normal conditions is between 12 and 24 months. John Kappenman is the engineer who has spent more time analyzing grid vulnerability to geomagnetic disturbance than almost anyone else in the field. His work, submitted to FERC and referenced in multiple congressional hearings, estimated that a Carrington-scale event striking the continental United States could damage or destroy between 300 and 365 large power transformers, representing somewhere between 60 and 70% of the nation's highest voltage transmission capacity. The restoration timeline under that scenario is not 9 hours. It is not 9 days. Independent technical assessments have suggested timelines ranging from 1 to 4 years for full grid restoration. Years. During which the downstream consequences for water treatment, for food refrigeration, for hospital operations, for financial infrastructure, compound in ways that are difficult to model and catastrophic to experience. I am going to name the uncertainty plainly here, because this channel does that. The event approaching Earth right now is not, by current models, a Carrington equivalent. The current modeling suggests a severe storm, G4 to G5 level, with the possibility of exceeding G5 parameters if the southward BZ is both strong and sustained. That is genuinely dangerous. It is not the same as the apocalyptic scenario in the paragraph above. But the same physical mechanism, geomagnetically induced current in long transmission lines flowing into high voltage transformers, operates at G4 and G5 in ways that cause significant damage even in the less severe storms of the 20th century. The scale is different, the mechanism is identical, and the grid has not gotten more resilient in the years since 1989. It has gotten more interconnected, which is both its great strength and, in a GIC event, its great vulnerability. The sun operates on an approximately 11-year cycle of activity, moving between solar minimum, when the solar disk is nearly quiet, few sunspots, few ejections, and solar maximum, when the surface is turbulent, sunspot groups are large and numerous, and major eruptive events become far more frequent. The cycle is driven by the differential rotation that tangles the magnetic field lines, and it resets when the global magnetic polarity of the sun reverses, which it does on average, roughly every 11 years. We are currently in solar cycle 25. The cycle number means it is the 25th solar cycle to be systematically tracked since the numbering convention was established. Cycle 25 began at solar minimum in December 2019. And here is what the data shows. It is running significantly stronger than forecasters predicted. The Solar Cycle 25 Prediction Panel, convened by NOAA and NASA, issued a consensus prediction in April 2019, projecting that Cycle 25 would be a below-average cycle, similar to the weak Cycle 24 that preceded it, with a predicted solar maximum sunspot number of 115. That prediction is not aging well. By mid-2024, the observed smooth sunspot number had already exceeded 180. The cycle peaked, or is near its peak, significantly stronger and earlier than the consensus forecast. Several independent research groups, including the team led by Scott McIntosh at the National Center for Atmospheric Research in Boulder, issued alternative predictions before the cycle began that tracked the actual observed behavior much more accurately. The consensus was wrong, the outlier predictions were right, and the consequence is that Earth has been exposed to a significantly more active sun than the official planning baseline assumed. Active region 12,960, the sunspot group on the solar surface responsible for producing both of the ejections now approaching Earth, has been categorized as a complex magnetically mixed region. The NOAA classification of its magnetic configuration at the time of the eruptions was beta gamma delta. If you don't live inside solar physics jargon, here is what that means. It is the highest complexity classification that solar magnetic configurations receive. Beta gamma delta regions are the ones that produce X-class flares, the most powerful category. They are the ones capable of launching full halo CMEs. They are the ones that, when they rotate into a position facing Earth directly, warrant the kind of operational attention that Boulder is paying right now. The region has produced multiple significant flares over the past week. Not all of them produced Earth-directed CMEs. Solar flares are not always accompanied by major ejections, and the geometry has to be right for a CME to hit Earth rather than another planet or the interplanetary medium in a direction away from us. But the region has been prolific. And the two ejections that form the basis of this investigation, the slower cloud launched first, the faster one behind it, both emerged from the same source region within a time window short enough to guarantee they would interact in transit rather than arriving separately days apart. This matters enormously for the severity of what arrives. A single CME from a region of this complexity, arriving cleanly without merger dynamics, would already be a significant space weather event warranting serious monitoring. The merger doubles the effective magnetic field strength in the combined sheath region. It amplifies the shock pressure at the leading edge. It extends the duration of high-amplitude field disturbance that Earth's magnetosphere will experience. Duration matters for geomagnetically induced current. The longer a strong southward BZ persists, the more heat accumulates in transformer cores. A brief spike of extreme BZ can be survived. A sustained period, 6 hours, 12 hours, 18 hours of strong southward BZ, is what overwhelms the grid. The Enlil model, the WSA Enlil cone model that NOAA's Space Weather Prediction Center runs to propagate CME forecasts from the Sun to Earth, is projecting arrival times with error bars that are operationally significant. The model has a known tendency to underestimate the speeds of fast CMEs. The physics of CME deceleration through the solar wind is complex, and the models handle it imperfectly. When the model is wrong about arrival time,
And that brings me to a thread of this investigation that I think most of the coverage is missing entirely, because the storm isn't just coming for the grid, it's coming for something up above the grid, something most people don't think about until it fails.
there are approximately 8,000 active satellites in Earth orbit right now. The exact count changes daily as new constellations are deployed, as older birds deorbit, as spacecraft enter safe mode or fail. But roughly 8,000. And in the next 48 to 72 hours, every single one of them will be exposed to a radiation and particle environment, unlike anything most of their operators have planned for. I want to take you through this carefully, because the satellite vulnerability story is one where the details matter enormously. Not all satellites are equally at risk. Not all failure modes are the same. And the cascading consequences of satellite degradation reach into daily life in ways that most people never trace back to their actual source. The first threat is the most direct, energetic particle events. When a solar flare erupts, it accelerates a subset of charged particles, primarily protons, to enormous velocities. And some of these particles, traveling near the speed of light, arrive at Earth in 8 to 30 minutes, long before the CME itself. These solar energetic particles, SEEBs, can penetrate satellite electronics, depositing energy in semiconductor devices, flipping bit states in memory, and in severe cases permanently damaging components through accumulated radiation dose. The flux of SEEBs associated with the event currently in progress has already been elevated. NOAA's GOES satellites, the geostationary operational environmental satellites that monitor the space environment from their positions 35,000 kilometers above the equator, are reporting proton flux levels that have crossed the threshold for a radiation storm classification. The second threat arrives with the CME itself. The passage of the compressed, turbulent sheath region through the near-Earth environment charges the surfaces of satellites unevenly. Different parts of the spacecraft acquire different electrical potentials. When the potential difference becomes large enough, electrostatic discharge events, essentially sparks, arc across internal components. These can look like random bit flips, like anomalous sensor readings, like command upsets that cause a spacecraft to enter an emergency safe mode. In safe mode, the satellite ceases normal operations, turns off non-essential systems, and waits for ground contact to diagnose the problem. A spacecraft in safe mode during the storm peak is unavailable for service. Multiply this by the constellation scale. But the third threat is the one that keeps satellite operators up at night, and it is the one that most directly connects to services most people depend on without thinking about them. Atmospheric expansion. Here is the physics. The Earth's upper atmosphere, the ionosphere and thermosphere, the tenuous region above roughly 80 kilometers where air is too thin to breathe, but still too thick for satellites to ignore, absorbs energy from the sun. During a severe geomagnetic storm, the energy input to the upper atmosphere increases enormously. The atmosphere expands, it puffs up. The altitude at which a given air density is found rises. Satellites in low Earth orbit, those flying below approximately 2,000 kilometers, suddenly find themselves moving through slightly denser air than before. That density increase, even at the level of a fraction of a percent of sea level pressure, is enormous compared to the near vacuum a satellite normally experiences. The drag increases, the satellite decelerates slightly, its orbit degrades faster. For most satellites, this is a manageable nuisance. They carry fuel for periodic orbital maintenance, and a few extra firings of the attitude control thrusters over the following weeks can compensate for the drag-induced decay. But Starlink's constellation, SpaceX's broadband internet satellite network, operates at altitudes specifically calibrated to minimize latency, between 500 and 600 kilometers. These altitudes are also precisely where atmospheric drag amplification from a major geomagnetic storm is most significant. In February of 2022, a moderate geomagnetic storm, not an extreme event, a KP of 5, a G1, struck shortly after a batch of 40 newly launched Starlink satellites was deployed. SpaceX reported that 38 of the 40 satellites re-entered the atmosphere and burned up because the atmospheric drag during the storm was too great for the spacecraft's low-thrust ion engines to overcome before orbital decay brought them down. 38 satellites lost, and that was at KP5. The storm currently projected is KP9, the maximum. The difference in atmospheric drag between a KP5 event and a KP9 event is not linear. It is exponential because the energy input to the upper atmosphere scales non-linearly with geomagnetic activity. The Starlink constellation has now grown to tens of thousands of spacecraft, many at those low altitudes, and SpaceX operates the largest satellite internet network on Earth. The company serves emergency responders, military operations, remote communities, and is increasingly embedded in critical infrastructure backup communications. A storm that replicates or exceeds the February 2022 drag event, but at KP9 rather than KP5, would almost certainly cost the network a significant fraction of its current constellation. The orbital mechanics alone guarantee it for spacecraft at the lower altitude bands. SpaceX has not publicly disclosed its current storm preparation protocols beyond generic statements about satellite operations during space weather events. The company did put spacecraft into safe mode and adjusted orientation during the large geomagnetic storm of May 2024, the G5 event that produced aurora visible across most of North America and much of Europe. That event, which I covered briefly in an earlier investigation, gave operators a partial rehearsal. But the storm in May 2024 arrived as a single complex structure from a series of CMEs that merged partially. The structure now approaching is a more classically defined cannibal merger, one faster ejection overtaking one slower ejection in transit, producing a denser, more compressed combined structure with a stronger shock. GPS is the other thread I need to pull here, because GPS failure during a major geomagnetic storm is one of the most consequential and least discussed failure modes in the entire event chain. GPS and its Russian counterpart GLONASS, the European Galileo system, and China's Beidou constellation, works by transmitting extraordinarily precise timing signals from satellites to receivers on the ground. Your navigation app on your phone, the precision agriculture systems managing automated farm equipment, the timing synchronization infrastructure underlying financial transaction networks, the approach guidance systems at airports. All of these and many more depend on receiving a clean GPS signal. And during a severe geomagnetic storm, the ionosphere, the electrically charged layer of the upper atmosphere through which GPS signals must pass, becomes a chaotic, scintillating mess. Ionospheric scintillation, rapid, irregular fluctuations in the signal strength and phase of radio waves passing through the ionosphere, caused by irregular electron density variations associated with geomagnetic storms. The scintillation can cause GPS receivers to lose lock on the satellite signal entirely. For a navigation app, this means the map freezes and displays your position incorrectly. For precision agriculture guidance on a 50-ton automated tractor, this means the machine doesn't know where it is. For the timing system at a financial exchange, this means transaction timestamps become unreliable. For an aircraft on instrument approach and low visibility, this means the approach guidance degrades exactly when it is most needed. The National Geodetic Survey and the FAA have protocols for GPS outage events, and major airports have backup navigation infrastructure. But those protocols assume localized or temporary degradation. A sustained, widespread ionospheric disruption during a prolonged extreme geomagnetic storm. And duration is the key word, because ionospheric recovery, after a severe storm, can take days, creates conditions that infrastructure has not been tested against at operational scale. And here is the compounding factor that I keep returning to in all of this. None of these failure modes, grid geek events, satellite drag, ionospheric disruption, electrostatic discharge, operates in isolation during an extreme geomagnetic storm. They operate simultaneously. The cascade is not grid failure, then satellite failure, then GPS failure. It is all of it at once, overwhelming the response capacity of the agencies and companies responsible for each piece of the system, at a time when those agencies and companies are also experiencing communication disruptions, because the very communication networks they depend on are part of the disrupted infrastructure. I said at the start that the faster storm catching the slower one produces something more dangerous than the sum of the two parts. I want to make good on that claim now, because the physics is worth understanding in some detail, and because understanding it changes how you think about the event unfolding right now. Think of each CME as carrying three things across interplanetary space. Plasma, which is just the raw mass of charged particles. Magnetic field, which is the invisible structure threading through the plasma, giving it direction and force. And kinetic energy, which is the sheer momentum of a billion-ton cloud moving at hundreds of kilometers per second. When two CMEs travel independently and arrive at Earth separately, a day or 2 days apart, Earth's magnetosphere deals with them sequentially. The magnetosphere is somewhat conditioned by the first storm. The geomagnetic activity index rises, the magnetosphere is compressed slightly, then it partially recovers. When the second storm arrives, the magnetosphere is still in a weakened state from the first, which makes the second storm's impact somewhat more severe than it would have been on a fresh magnetosphere. This is already known to amplify geomagnetic storm intensity, compared to what either event alone would produce. Forecasters call it preconditioning, but a cannibal CME does not give the magnetosphere time to precondition. The merger happens in transit before either structure arrives. And the merged structure is not simply two CMEs added together. Here is what the interaction produces. When the faster ejection's shock front slams into the slower ejection's trailing edge, it compresses the plasma between the two shocks into an enormously dense slab, sometimes called the merged interaction region. This compressed slab has a magnetic field amplitude, the strength of the field measured in nanoteslas, that can be 2 to 4 times stronger than either original CME's field measured in isolation. The compression is not just additive. It is multiplicative because you are forcing the same number of magnetic field lines into a smaller volume. Field lines don't disappear when two structures collide, they pile up. And piled up field lines in a smaller volume means stronger field. The DST index, the disturbance storm time index, which measures the horizontal component of the Earth's magnetic field at the equator and is the primary indicator of geomagnetic storm severity, scales roughly with the square of the compressed magnetic field strength in the merged sheath for extreme events. The relationship is not perfectly square, but the point holds: double the field, more than double the storm. Triple the field, more than triple the storm. The compression dynamics of a cannibal CME can push the effective field strength far beyond what you'd add up by summing two separate storms. There is a second amplification mechanism that is less intuitive. The merged sheath region, the turbulent, compressed zone between the leading shock and the core of the original faster CME's flux rope, is extended in time relative to a single CME's sheath. When a single CME arrives, the sheath passes in perhaps 1 to 3 hours, followed by the smoother flux rope of the ejection itself. In a cannibal structure, the sheath region is thicker because it contains the compressed remnants of the first CME mixed with the sheath material of the second. This extended sheath is turbulent. The field orientation rotates, spikes, and reverses, which means the magnetosphere is subjected to prolonged exposure to a fluctuating, high-amplitude field. For grid operators, this duration matters in a very specific way. The geomagnetically induced currents in long transmission lines are proportional to the rate of change of the magnetic field. A sudden spike and retreat produces one set of transformer conditions. A sustained period of strong, fluctuating field, the kind the cannibal sheath produces, subjects transformers to repeated cycles of thermal stress without recovery time. Each cycle heats the transformer's core. Without cooling time between cycles, the heat accumulates. The question of whether a transformer survives is in part a question of how long the bad conditions last. The USGS, the United States Geological Survey, which operates a network of magnetic observatories across North America, is right now recording baseline geomagnetic field measurements that will be compared against the storm time measurements when the event arrives. The USGS Observatory at Fredericksburg, Virginia, site code FRD, is one of the most operationally relevant for the eastern seaboard grid. So is the observatory at Boulder, Colorado, site code BOW. So is Sitka, Alaska, SIT, which sees the most extreme variations because of its high latitude. When the storm arrives, the rate of change of the field at these observatories, expressed in nanoteslas per minute, NT per minute, will be the real-time measure of how hard the grid is being hit. The threshold that engineers treat as a serious alarm level for GIC events in the eastern United States is roughly 400 nanoteslas per minute. The Halloween storms of 2003, which damaged transformers in South Africa and produced GIC events across Sweden and other high-latitude regions, produced rate of change values exceeding 2,500 nanoteslas per minute in some locations. The Carrington event, extrapolated from available data, may have produced values 10 to 20 times that. I am spending this much time on the physics because I think it matters for how you hold the uncertainty about this event. We don't know yet what the BZ orientation will be. We don't know exactly how fast the merge cloud is moving. The models have error bars. We don't know whether the trailing faster ejections flux rope or the leading slower ejections flux rope will dominate the structure of what arrives. All of these things are uncertain. What is not uncertain is that a cannibal CME arrival produces the specific amplification mechanisms I have just described, and that those mechanisms, in a severe event, can drive transformer thermal stress in ways that 90 minutes of a Quebec scale event does not. And this is where the investigation takes a turn that most of the coverage of this event has completely missed. Because when I went through the technical literature on cannibal CME impacts, not just the popular science coverage, but the peer-reviewed papers from the journal Space Weather, the AGU journal Geophysical Research Letters, and the technical assessments published by NERC, I found something that the public narrative almost never includes. Something that changes how you think about the grid risk specifically. The vulnerability of the North American power grid to geomagnetic storms is not uniform. It is profoundly specifically geographic. And the geography, when you look at it against the physics, is alarming in a way that the aggregate statistics conceal. Geomagnetically induced currents are amplified by two geographic factors acting together. The first is latitude. Higher latitudes see stronger and more rapid magnetic field variations during geomagnetic storms because they are closer to the geomagnetic poles where the field disturbance is most intense. This is why Quebec, at roughly 46 to 52 degrees north latitude, was hit harder in 1989 than, say, Miami. But the second factor is geology, and this is the one that gets almost no attention. The conductivity of the Earth's crust determines how easily geomagnetically induced currents can flow through it and into surface infrastructure. Thick, geologically ancient igneous and metamorphic rock. The Canadian Shield, for example, extending south through Minnesota, Wisconsin, and into New England, is an extremely poor conductor. It has very high resistivity. And high resistivity ground forces the induced currents that would otherwise flow harmlessly through the ground to flow instead through the nearest available conductor, the power lines and pipelines sitting on top of it. This is the specific mechanism that made the Hydro-Quebec outage so severe. Quebec sits atop the Canadian Shield. The storm-induced currents had nowhere to go but into the grid. And as it happens, the New England and Mid-Atlantic states, heavily populated, densely connected to the national grid, dependent on a small number of large transformers at key substations, also sit near or on the southern extension of this resistant geological formation. The region that combines high-latitude magnetic disturbance with high ground resistivity, and therefore highest GIC coupling into the grid, runs from Manitoba through Ontario, through Quebec, through the northeastern United States, and diagonally south through the Appalachian Corridor. The storm arriving in the next 48 to 72 hours, if it delivers G5 conditions, will produce the highest GIC amplitudes in exactly this corridor. Not in Florida, not in California, in the Northeast and Northern Midwest. The region with the highest population density in North America. The region where grid restoration capacity is most constrained by geography and by the density and complexity of the existing infrastructure. A study published in the journal Space Weather by Antti Pulkkinen and colleagues at NASA Goddard Space Flight Center modeled the GIC response of the North American grid to a Carrington equivalent event. The study found that the highest risk substations, the ones most likely to experience transformer thermal damage, were concentrated in the Canadian provinces and the northeastern United States, with a secondary cluster in the upper Midwest. This is not a coincidence. It is geology meeting physics meeting grid architecture. And none of that has changed since the study was published. The grid in those regions, if anything, is more heavily loaded now than when the modeling was done. The Federal Energy Regulatory Commission issued Order 830 in 2016, requiring transmission system owners to develop and implement plans to protect against geomagnetic disturbance. Industry compliance has been documented, reports have been filed, procedures have been written. But the order requires that operators be able to continue operating during a 1-in-100-year storm. The question that engineers have raised in subsequent technical forums is whether the event currently approaching represents the kind of scenario the order was designed against, or whether it represents something above that design baseline. That question does not have a clean answer yet because we do not yet know the full magnitude of what is arriving. But I will say this. The combination of the Northeast geological amplification factor, the grid's geographic concentration of critical transformers in the highest risk zone, and the specific compound nature of this cannibal event is not a combination that appears frequently in space weather history. The last time conditions approached this conjunction of factors in the Northeast was the 1989 event, and that storm, as severe as it was, did not deliver the sustained high southward BZ duration that a fully formed cannibal CME can produce. The Quebec outage was 9 hours. It was caused by relay tripping, not transformer damage. The transformer survived. That is the margin that currently exists between a disruptive but recoverable event and something significantly worse. October 28th through November 4th, 2003. Space weather engineers call this the Halloween storm sequence, partly because of the calendar and partly because of what it revealed about grid vulnerability. A series of major solar flares and CMEs erupted from the same active region over approximately 1 week. The largest flares were among the most energetic ever recorded, X17 and X28 on the NOAA flare intensity scale. The CMEs arrived in a rapid sequence that preconditioned the magnetosphere and produced extended periods of geomagnetic activity at G4 and G5 levels. The KP index reached 9, the maximum, on multiple separate occasions during the event sequence. The operational consequences were substantial and specific. 15 satellites reported anomalies or failures during the event. The Adios 2 satellite, a Japanese Earth observation spacecraft, lost power and was never recovered. The Midori 2, also Japanese, failed completely. Multiple other spacecraft suffered component damage from radiation and electrostatic discharge. The Mars Odyssey spacecraft at Mars experienced a radiation dose that damaged its star tracker camera, the exposure at Mars, from a storm centered at the Sun. For aviation, the event forced the FAA and its international counterparts to redirect polar routes. Flights that cross the Arctic between North America and Asia routinely use these routes because they are geographically shortest. But during severe particle radiation events, the radiation exposure to passengers and crew at polar altitudes becomes significant, and HF radio communication blackouts along polar routes are operationally grounding. More than 100 polar flight paths were rerouted during the Halloween sequence. In Sweden, an area of about 50,000 customers lost power after a large transformer failure at the Malmö substation was attributed to the geomagnetically induced currents from the storm. It was one of the first documented modern cases of a GIC-caused transformer failure in a developed country grid, not a relay trip that could be reversed, but actual thermal damage. The transformer was taken out of service. Engineers at the Swedish grid operator spent the aftermath analyzing what had happened, and what they found confirmed the theoretical models. The failure occurred during a period of sustained, high-amplitude geomagnetic field variation, consistent with transformer core heating by repeated half-cycle saturation cycles. In South Africa, the damage was more extensive. South Africa's grid at the time had a configuration that made it particularly vulnerable. Long transmission lines, relatively poor GIC mitigation infrastructure, and a position at a geographic latitude where the storm produced significant effects despite being in the southern hemisphere. Multiple transformers in the Eskom network were damaged. One large transformer at the Matimba power station required replacement. The replacement process took more than a year and required importing a transformer that met the precise specifications. Monika Korda at the GFZ German Research Center for Geosciences published analysis of the Halloween storm's ground magnetic field effects across Europe, confirming that the rate of change of the field at Scandinavian observatories reached levels previously seen only in the very largest recorded storms. The peak dBddt values, that rate of change measurement I mentioned earlier, were in the range that the theoretical models had identified as potentially damaging for long transmission systems. The Halloween storms of 2003 hit during solar cycle 23, a relatively strong cycle. We are currently in solar cycle 25, which is proving to be stronger than predicted. The active region responsible for the current event has been producing X-class flares. The merged CME structure approaching Earth has the profile, speed, compression, likely field magnitude, of an event that sits in the upper range of what modern space weather forecasting has operationally encountered. The difference between the Halloween storms and the event now approaching is not necessarily the maximum intensity. It may be the duration. The Halloween sequence stretched over days, but the individual storm impacts were separated by partial recovery periods. A single, massive cannibal CME can deliver an extended period of concentrated, sustained extreme field activity, a single punch rather than a series of blows, with the specific property that the compressed sheath from the merger sustains the high amplitude disturbance for longer than a typical single CME event. That extended duration is the specific physical property that engineering models flag as most damaging to transformer thermal health.
And one more thing that I think is important to say clearly. The transformers that failed in South Africa in 2003 have mostly been replaced. The modeling that Kappenman and others have done since then has been incorporated into some grid operator planning. Some mitigation measures have been implemented, some. But the North American grid has thousands of large power transformers, and the fraction that have been retrofitted with GIC blocking devices or neutralizers remains, by the most recent public reporting from NERC, a minority of the total critical infrastructure. The gap between what exists and what the engineering community has recommended for full mitigation is not closed. It remains open as this storm approaches.
The timeline is now inside the operational window. This is where the investigation shifts from mechanism and history to immediate reality, not projection, reality. What is happening, what will happen, and when? The Discover satellite at the L1 point will be the first to register the arrival of the merged shockwave. The Discover magnetometer and Faraday cup plasma sensor are the real-time sentinel for Earth. When the shock arrives at L1, the data will show a sudden commencement, a sharp jump in solar wind speed and magnetic field magnitude that will be instantly recognizable in the raw data stream. That data streams to the Space Weather Prediction Center in Boulder in near real time, latency of a few seconds. The forecasters will see it as it happens. From that moment, the Earth has roughly 15 to 60 minutes before the shockwave arrives at the bow shock of the magnetosphere, the outer boundary of Earth's magnetic influence, approximately 60,000 to 80,000 kilometers upstream on the sunward side. The 15-minute end of that range applies to fast, dense events where the solar wind has been cleared, and transit from L1 to the magnetopause is rapid. The 60-minute end applies to slower, denser events where the upstream interaction takes longer. With a cannibal merger traveling at the speed currently projected, the 15-minute end of that range is operationally more relevant than the 60-minute end. 15 minutes is not a lot of time. I want to be very direct about this because I think it is the single most important operational fact in the entire event. 15 minutes is not enough time to perform an orderly shutdown of a large high-voltage transformer to protect it from a GIC surge. The process of isolating and de-energizing major transmission substations takes hours, not minutes, and must be coordinated across a network where every action has downstream consequences for adjacent nodes. What 15 minutes is enough time for is alerting operators, activating emergency protocols, and, in systems that have automated GI protection devices installed, confirming those devices are operating. The Space Weather Prediction Center will issue G5 geomagnetic storm watches and warnings through the NOAA alert system, through the emergency alert system, and through direct contacts with power utilities, pipeline operators, satellite operators, and the Federal Emergency Management Agency. The warning system works. The warnings will go out. The question, and this is an honest question with an honest, uncertain answer, is what response capacity exists on the receiving end. Major independent system operators, the ISOs and RTOs that manage regional electricity markets and grid reliability across North America, including PJM interconnection covering the Mid-Atlantic and Midwest, the Mid-Continent ISO and ISO New England, have storm operation procedures. They can instruct member utilities to increase reactive power reserves, to desynchronize certain long transmission paths that are known to be high GIC risk, and to pre-position restoration resources. These are real tools with real effect. They reduce the risk, they do not eliminate it. The honest assessment of what the next 72 hours holds has 3 distinct phases, and I am going to walk through each one clearly. Phase 1 is the pre-arrival period, right now through the impact. The primary activities are monitoring, confirmation, and alerting. NOAA forecasters will be tracking Discover data every second. The ACE satellite at L1, the Advanced Composition Explorer, an older but still operating solar wind monitor, provides backup measurements. The Space Weather Prediction Center will update its forecasts hourly and will issue special alerts as the situation evolves. Grid operators receiving those alerts have the most time they will have to take protective action. Whether they take action is a function of what their operating procedures authorize and what the real-time conditions are. Phase 2 is the storm main phase, the period after arrival during which the DST index is dropping, becoming more negative, indicating the development of the ring current around the Earth and the compression of the magnetosphere. This is the period of maximum geomagnetic activity. During the main phase, the rate of change of the ground magnetic field is highest. GIC in transmission lines is highest. Ionospheric disruption is most severe. Satellite operations are most compromised. And this is when the failures, if they occur, will occur. The main phase of a severe cannibal CME event can last 6 to 12 hours, potentially longer if the merged structure is unusually thick and the southward BZ is sustained. Phase 3 is the recovery phase, the period after the storm's peak when the DST index slowly returns toward normal. The magnetosphere gradually expands back to its quiet time configuration, and the induced currents in the grid diminish. Recovery from a G5 event typically takes 1 to 3 days for the geomagnetic field to return to baseline. Ionospheric recovery, particularly at mid-latitudes, can take days to a week. The infrastructure consequences of whatever happens during the main phase will be the focus of Phase 3, and in a scenario involving transformer damage, the timeline of infrastructure recovery extends far beyond the timeline of geomagnetic recovery. I have been deliberately specific about what is known and what is uncertain throughout this investigation, so let me do the same here. It is not certain that this event will cause transformer damage in North America. The probability of a transformer damaging outcome depends on the actual southward BZ magnitude and duration, which we won't know precisely until Discover sees the arrival. The specific GIC coupling at each substation, which varies by location and local ground resistivity, and whether the protection and mitigation measures that utilities have in place are adequate to limit transformer heating below the damage threshold. All three of those factors have uncertainty. What is certain is that the physical conditions for a damaging event, fast merge structure, likely strong southward field, known grid vulnerability in the northeast, are in place. The uncertainty is whether the actual values will be at the severe end of the forecast range or the very extreme end. I want to do something in this section that documentary investigations rarely attempt. Give you a regional picture of where the specific risks are concentrated and what they mean for people living in those areas. Not as fear, but as operational information that a person can actually use. The northeast of the United States and the Canadian provinces of Ontario and Quebec carry the highest combined risk from this event for the reasons I explained in the geological amplification section. High magnetic latitude, high ground resistivity, long transmission lines, and a concentration of critical infrastructure that is already at capacity. If you live in New England, Massachusetts, Connecticut, Vermont, New Hampshire, Maine, you are in the highest risk geographic band for GIC-driven grid disruption. This does not mean the lights will definitely go out. It means that if the event reaches the high end of the forecast range, the northeastern grid is the most vulnerable to it. What does a major regional outage in the northeast look like in practice? In winter, heating is the immediate concern, both electric heat and the electric controls on gas heating systems. Water systems are the second concern. Municipal water pumping systems require electricity, and a major outage that lasts more than a few hours begins straining backup power at water treatment and pumping facilities. Communications is the third. Cellular towers have battery backup typically rated for 4 to 8 hours, after which they require diesel generator operation. Hospital and emergency services have generator backup, but generators require fuel, and fuel supply chains depend on functional payment infrastructure and logistics coordination, both of which are degraded in a major multi-area blackout. The upper Midwest, Minnesota, Wisconsin, Michigan's Upper Peninsula, is the secondary risk zone for similar geological reasons. The Canadian Shield extends into these states, and the region is geographically at higher magnetic latitude than the mid-Atlantic. Major transmission infrastructure serving the Twin Cities and the upper Midwest runs through this zone. The Pacific Northwest carries elevated risk for a different reason. The region's grid is dominated by hydroelectric power, with long transmission lines running south and east from dams in the Columbia River system. Those long lines are efficient GIC antennae, and the Pacific Northwest sits at relatively high latitude. The Bonneville Power Administration, which operates the transmission system in the region, has been involved in NERC's geomagnetic disturbance work and has specific storm operation protocols. The southeast Florida, the Carolinas, Georgia, carries lower GIC risk because of lower magnetic latitude and because the geology of the coastal plain is relatively conductive, which shunts induced currents into the ground rather than into transmission lines. Lower risk does not mean no risk. The ionospheric disruption from a G5 event will affect all regions equally, and the GPS and communication impacts are not geographically limited in the way GC impacts are. If you are in a high-risk region, and you want to do something practical in the next 24 to 48 hours, the list is not glamorous. Know where your manual can opener is. Know where your flashlight and batteries are. Have enough water stored for 3 days. 1 gallon per person per day is the standard emergency planning guideline. Know whether your heating system requires electricity to operate. Charge your devices fully. If you have prescription medications that require refrigeration, know what the storage guidance says about limited time at room temperature. None of this is dramatic. All of it is sensible for any multi-day power outage scenario, storm-related or otherwise. I have to take some time here to address specific claims that are circulating about this event, because they are circulating loudly and because the people making them are reaching a real audience, and those people deserve an accurate picture rather than a fabricated one. And the accurate picture, as it happens, is alarming enough without embellishment. The first claim, that HAARP, the High Frequency Active Auroral Research Program, currently operated by the University of Alaska at the facility in Gacona, Alaska, is somehow responsible for triggering or amplifying the current solar event. This claim appears in multiple forms, ranging from HAARP caused the CME to erupt, to HAARP is being used to steer the storm toward populated areas. Let me kill this with specific physics, because that is the only thing it deserves. HAARP's maximum total radiated power is 3.6 megawatts. The total electromagnetic energy contained in a major coronal mass ejection, the kinetic energy of the plasma plus the magnetic field energy in the flux rope, is on the order of 10 to the power of 25 joules. That is 10 million billion joules. The ratio between HAARP's power output and the energy of the event it is alleged to have caused or directed is approximately a factor of 10 to the power of 21, roughly 1 sextillion. This is not a meaningful comparison. It is the difference between a birthday candle and the sun. Less than the difference between a birthday candle and the sun. HAARP cannot steer, amplify, or initiate a coronal mass ejection, or any fraction of one, under any physical theory that has a relationship to observed reality. The facility's actual purpose, studying ionospheric physics by transmitting radio waves into the ionosphere and observing the response, is legitimate science, and the research it supports is published in peer-reviewed literature. The second claim, that governments or military agencies have advanced knowledge of this event that they are concealing, and that early warnings have been suppressed. This one is easier to address than the HAARP claim because it is self-refuting by the public record. The NOAA Space Weather Prediction Center publishes its forecasts, model runs, alert thresholds, and raw data streams publicly, in near real time, accessible to anyone with an internet connection. The European Space Agency Space Weather Service Network does the same. The USGS publishes its magnetometer data in real time. The output of the Enlil solar wind propagation model is publicly available. I have been reading all of this openly, without special access, as part of researching this investigation. There is no concealment because there is no concealed channel. The data infrastructure is built on open science principles. The warnings are being issued, they are public. The question is whether the people who need to act on them are acting, which is a different problem from concealment. The third claim, that the severity of this event is being downplayed by official sources to prevent panic. This one deserves more careful treatment because it is the most sophisticated of the three, and it touches on a real tension in emergency communication. There is a legitimate critique embedded in this claim, not the interpretation, but the observation that motivates it. Official communications about space weather events do, sometimes, lead with reassurance rather than specificity. There are reasons for this that are not sinister. Emergency managers are trained to communicate in ways that support orderly protective action rather than disorderly panic. A message that says the grid could collapse for months is operationally useless if it produces mass runs on grocery stores and fuel stations, rather than the specific preparedness steps that actually reduce vulnerability. The communication constraint is real, but there is a difference between calibrated communication and suppression. The official NOAA G5 watch that has been issued for this event is the highest category alert in the space weather warning system. G5 watches are rare. They have been issued fewer than 10 times in the history of the current alert scale. The documentation accompanying a G5 watch, which is publicly available, specifically mentions power grid collapse as a potential outcome. The warning is there. It is public. Whether the media coverage of the warning has conveyed its full gravity is a media critique, not a suppression critique. And I think that media critique has merit, which is in part why this video exists. The honest steelman of the concern underlying the suppression claim is this: the full consequence cascade of a major grid JICE event, the transformer damage, the multi-month restoration timeline, the downstream consequences for critical services, is genuinely underrepresented in mainstream space weather communication. Not because of malice, but because the communication is built around the geomagnetic storm itself, and the infrastructure consequence chain extends far beyond what a space weather alert system is designed to address. The storm warning says G5. It does not say, and here's what G5 means for your water supply. That gap is real, and it is worth naming. But it is not the same as saying that officials know the truth and are hiding it. There is a final historical case study I want to bring in here, because it is the most operationally relevant parallel to what is currently approaching, and it is not well known outside the space weather community. On July 23, 2012, the Sun launched a coronal mass ejection from active region 11,520. The ejection was remarkable by any measure. The velocity of the leading edge was estimated at approximately 2,500 kilometers per second, comparable to estimates of the Carrington Event. The magnetic field in the sheath region, measured by the Stereo A spacecraft, which happened to be positioned in the path of the ejection, exceeded 200 nanoteslas in the compressed sheath. The Stereo A measurements confirmed that the July 2012 event had the physical properties, speed, field magnitude, likely southward BZ duration, to produce a geomagnetic storm broadly comparable to Carrington in intensity. But Stereo A is not Earth. The ejection missed our planet by 9 days in orbital position. Earth had been at that location 9 days earlier and had moved on around the Sun. The event did not hit the Earth. It hit Stereo A, which was not critical infrastructure, and the measurements it made were invaluable scientific data rather than an operational catastrophe. Daniel Baker at the University of Colorado Boulder, who directs the Laboratory for Atmospheric and Space Physics, and is one of the foremost experts in space environment effects on technological systems, described the July 2012 event in these terms. If it had hit Earth, it would have been the most powerful geomagnetic storm in the history of the modern technological era. He added in a paper published in Space Weather in 2013, an estimate that he characterized as conservative. The damage to power grid infrastructure and other technological systems could have resulted in a bill of recovery costs in the range of $1 to $2 trillion. Trillion for the United States alone, with recovery timelines measured in years, 9 days. That is the margin by which the modern electrical civilization avoided its most serious test. 9 days in the orbital position of Earth along its path around the Sun. The event now approaching is not the July 2012 event. The speeds are lower, the distances different, the structure somewhat less extreme by current measurements. But the July 2012 case study is important not because it is equivalent to what is coming, but because it establishes a concrete recent precedent for exactly the type of event, cannibal CME equivalent extreme storm, that the current situation is approaching from below. The physical mechanisms that would have made July 2012 catastrophic are the same physical mechanisms operating in the event now approaching, at a somewhat lower intensity. Understanding the July 2012 case is understanding the upper boundary of what extreme versions of this type of event can do. And it happened in 2012, 13 years ago. The Sun is more active now in cycle 25 than it was in cycle 24 when the July event occurred. The conditions for a repeat of that type of event, perhaps not at that peak intensity, but in that physical category, are better now than they have been at any point since the 2012 near miss.
Nature Communications. Their conclusion, and I am going to give you the substance of it without the academic hedging because this is what the data says, was that the event was a compound cannibal type structure, that it carried one of the highest solar wind dynamic pressures ever directly measured by a spacecraft, and that had it struck Earth with the southward BZ orientation that Stereo A measured, a geomagnetic storm of DST values exceeding negative 500 nanoteslas was physically plausible. The DST record minimum ever measured at Earth is approximately negative 589 nanoteslas from the March 1989 storm. The July 2012 event, had it struck Earth, might have approached or exceeded that level. 9 days.
There are 3 ways to honestly hold what the data is telling us about this event. 3 interpretations that the evidence can support, each of them grounded in the physics, each of them carrying different implications. I want to give each one its full weight, because this channel does not cherry-pick the alarming reading and pretend the other readings don't exist. The most frightening interpretation is not automatically the correct one. The evidence decides. The first interpretation is the most reassuring, and I want to give it the seriousness it deserves. Not as a straw man, not as a way to preemptively dismiss it, but because the data genuinely supports it. Under this interpretation, the merged CME structure arrives with strong but southward BZ that is significant in magnitude, perhaps 100 to 150 nanoteslas, but which does not sustain for the extended period needed to drive transformer heating into the damage threshold. The storm produces G4 to G5 geomagnetic conditions. It causes widespread aurora visible across the continental United States and Europe. It produces HF radio communication blackouts for hours and disrupts GPS accuracy for navigation and precision applications. It stresses satellite operations and may cause some anomalies and safe mode entries. The grid experiences significant GIC events in the high-latitude regions, the Northeast, the Upper Midwest, the Canadian provinces, and some protective relays trip, causing temporary, localized outages that are restored over a period of hours using established procedures. This is not a trivial event under this interpretation. It would be the most significant geomagnetic storm to impact modern infrastructure in decades. It would produce real economic costs, real disruption to navigation and communication, and real stress on the grid. But it would not cross the threshold into transformer thermal damage. The key physical factor that makes this interpretation plausible is the duration of the southward BZ. Even a very strong BZ, strong magnetic field pointing south, does not cause transformer core heating past the damage threshold if it only lasts 2 to 4 hours. Short duration, high amplitude. The grid flexes but does not break. The argument for this interpretation rests on two physical considerations. First, the flux rope orientation of a cannibal CME is genuinely uncertain, and there is a meaningful probability, not a slim one, that the merged structure arrives with a northward BZ or a rotating BZ that spends significant time pointing north. If the initial sheath has southward BZ, the subsequent flux rope rotation could reduce the total duration of extreme southward exposure. Second, the speed of the structure. Fast impacts produce impulsive but brief intense field variations, while slow impacts produce prolonged sustained disturbances. A fast impact at the speed currently projected may actually be shorter in duration than a moderate speed event because the structure passes through more quickly. Janet Luhman at the Space Sciences Laboratory at UC Berkeley has spent decades studying how CME structures evolve during transit, and her work has repeatedly confirmed that in transit evolution, the rotation and deformation of the flux rope during the journey from Sun to Earth is one of the largest sources of forecast uncertainty for geomagnetic storm intensity. The magnetic field orientation at L1 is not reliably predictable from observations of the solar source region. This genuine scientific uncertainty cuts in both directions. It could be worse than expected, but it could also be better. Under the first interpretation, it turns out to be better, or at least not worse. This interpretation is consistent with the data. It is fairly held, and it may be the one the next several days confirm. But it requires that the merged sheath region, the most compressed, most magnetically amplified part of the structure, delivers a southward BZ that is either not as strong as the compression physics suggests, or not as sustained as the structure's thickness would imply, or both. Those are meaningful conditions. They are not impossibly optimistic, but they require the event to cooperate with the best case reading of the uncertain parameters. The second interpretation is where the weight of the peer-reviewed literature on cannibal CME events actually points, and I think it deserves the most time of the three. The intermediate interpretation says this: the merged structure arrives with a sustained southward BZ in the range of 150 to 250 nanoteslas, persisting for 6 to 12 hours during the main storm phase. The DST index reaches between -300 and -450 nanoteslas, placing the event in the same intensity class as the 1989 Quebec storm, but potentially exceeding it. GIC in the northeastern United States and Canadian provinces reaches values that push transformers at the most vulnerable substations into repeated thermal stress cycles. Some transformers sustain damage that takes them out of service for days to weeks. Others survive. The grid in the most affected region experiences a combination of protective relay tripping and, in a subset of cases, sustained abnormal loading conditions that require operators to manually de-energize transmission paths. Restoration takes days, not hours, in the hardest hit areas. Under this interpretation, the satellite consequences are significant. A meaningful fraction of Starlink satellites in low Earth orbit experience drag-induced orbital decay that requires de-orbit. GPS accuracy is degraded across North America and Europe for 2 to 5 days as the ionosphere slowly recovers. HF radio, used by aviation, maritime operations, military communications, and shortwave broadcasting, is blacked out at high latitudes for an extended period. Polar flight routes remain closed for 24 to 72 hours. This interpretation is supported by the physics of cannibal CME structures specifically. Kazuoki Murasaki and colleagues at JAXA, the Japan Aerospace Exploration Agency, published analysis of cannibal CME events in the Space Weather Journal, finding that the compressed sheath region in a merger event consistently shows amplified southward BZ components compared to individual CME sheaths. The amplification factor in the analyzed events ranged from 1.5 to 3 times the individual CME values. At the lower end of that range, applied to the field estimates for the current event, the southward BZ could be in the 100 to 150 nanotesla range, manageable under the first interpretation. At the upper end, the values would be in the range associated with DST excursions beyond negative 300 nanoteslas, firmly in the second interpretation's territory. The second interpretation also draws support from the geological amplification analysis I described earlier. Pulkkinen's modeling of the North American grid's GIC response to an event in this intensity class showed transformer thermal stress accumulations in the northeast reaching values within the range of historical failure thresholds, not certain failure, but within that range at specific substations identified in the model as highest risk. And here is the honest implication of the second interpretation that I don't want to understate. Even under the moderate reading of this event, the consequence chain for the most affected region includes multi-day power outages affecting millions of people, significant satellite service disruptions affecting communications and navigation, and the near-certain loss of HF radio across polar latitudes for an extended period. A multi-day regional power outage in winter or in summer heat is not a minor inconvenience. It is a serious public health and infrastructure event. The second interpretation is not catastrophic at a civilizational scale, but it is seriously bad for the specific regions in the highest impact zone. And it is the interpretation that the combination of the physical structure, the geological amplification, and the known grid vulnerability most directly points toward. The third interpretation is the one I am going to present with the most care, because it is also the one most vulnerable to sensationalism. And this investigation is not in the business of sensationalism. So I am going to state what the physics allows, ground it in specific evidence, and then tell you exactly what would have to be true for it to be correct. Under the third interpretation, the merged structure delivers a sustained southward BZ in the range of 250 to 400 nanoteslas or beyond, persisting for 12 to 24 hours during the main storm phase. The DST index reaches negative 450 to negative 600 nanoteslas, approaching or exceeding the historical record minimum. GIC in the northeastern United States and Canadian provinces reaches values that, in combination with the sustained duration, push multiple major transformers at critical substations past the thermal damage threshold. The number of damaged transformers is not in the hundreds, that is the Carrington equivalent scenario, but it is enough to destabilize large portions of the northeastern and upper Midwest grid for a period that extends beyond what can be bridged by backup generation and mutual aid. Restoration takes weeks rather than days in the most affected areas. Satellite losses are substantial. The Starlink constellation loses a large fraction of its low Earth orbit assets. Other commercial and government satellites in low Earth orbit are degraded or destroyed. GPS is unreliable across mid-latitudes for a week or more as the ionosphere recovers. Financial market operations are disrupted by timing infrastructure failure. Emergency communications are severely compromised as cellular and HF systems fail simultaneously. For this interpretation to be correct, the following physical conditions must hold simultaneously. The southward BZ in the compressed sheath must be at the upper end of the forecast range. The southward component must not rotate northward for an extended period, meaning the flux rope must maintain unfavorable polarity throughout the main phase, and the GIC coupling in the most vulnerable substations must be at the upper end of the modeled range, which depends on the local ground resistivity and the specific transmission path loading at the time of arrival. What makes this interpretation physically plausible is the amplification argument from the cannibal merger. The July 2012 event demonstrated that the compressed sheath of a fast cannibal structure can reach field magnitudes well above 200 nanoteslas at the measurement point. Stereo A measured sustained values in that range during the July 2012 transit. Applied to Earth, with the known GIC coupling factors in the northeast, that magnitude of field, sustained for 12 or more hours, exceeds the threshold that engineering models identify as the damage range for the most vulnerable transformers. What makes it less likely than the second interpretation is the cumulative requirement. Every uncertain parameter must simultaneously resolve at its worst value. The BZ must be maximally southward, not just significantly southward. The duration must be at the long end of the range, not the moderate end. The grid conditions at the time of arrival, how loaded the transmission paths are, whether operators have taken any preemptive protective action, must be at maximum vulnerability. The probability of all three simultaneously is lower than the probability of each individually. This is why the second interpretation carries more weight than the third in any rigorous probabilistic assessment. But lower probability is not zero probability, and the asymmetry of the outcomes is worth stating plainly. If the first interpretation is correct and we treated it as the second, the cost is some operational inconvenience and economic disruption from precautionary measures. If the third interpretation is correct and we treated it as the first, the cost is potentially years of partial grid function in the most affected region, with all the downstream consequences that implies. The asymmetry matters for how societies and infrastructure operators should weight their responses under uncertainty. Let me be as precise as I can about the three categories of knowledge that exist right now, because I think the precision is more useful than any summary. What is confirmed fact, not interpretation? A cannibal CME event is in progress. The merged structure is approaching Earth. The physical mechanism, faster ejection overtaking slower ejection, compression of the magnetic field in the merged sheath, amplification of the combined field magnitude, has been observed in multiple prior events and is well established in the scientific literature. The NOAA G5 watch is the highest category alert in the space weather warning system and reflects a genuine assessment of potential storm severity. The grid in the northeastern United States and Canadian provinces is the highest risk zone for geomagnetically induced current damage, based on both the magnetic latitude and the geological amplification from the resistive Canadian shield. Large power transformers, if thermally damaged by GIC, cannot be replaced on short timescales. The July 2012 near miss demonstrated that events in this physical category have occurred within the last 15 years and could occur again. What is genuinely uncertain? The southward BC magnitude and duration that the merged structure will deliver at Earth. This will not be known until DSCOVR measures it approximately 1 hour before impact. The exact timing of the impact within the 48 to 72 hour window from the initial ejection. Whether any transformer damage will occur, and if so, where and how many units are affected. Whether protective relay tripping events cascade in a way that causes widespread outages or remains localized and recoverable. What specific data would resolve the uncertainty? The DSCOVR real-time solar wind data stream, specifically the BZ value from the magnetometer, is the single most important number in the entire event. When that number goes strongly negative, southward, and the hour counter starts, the operational response window opens. Second, the rate of change of the geomagnetic field at the USGS observatories at Fredericksburg, Virginia, Boulder, Colorado, and Sitka, Alaska. When those values exceed 400 nanoteslas per minute, the GIC event is within the serious damage range for vulnerable substations. Third, transformer health monitoring data from the utilities in the highest risk zones, data that is not publicly available, but that grid operators are watching in real time. I want to name something honestly here. The three questions above are answerable by the data, and the data is coming. Within 72 hours, the uncertainty about this specific event will be resolved by observation. Either the storm delivers the worst-case BZ and the grid response confirms the worst-case outcome, or it doesn't. Reality will adjudicate between the interpretations. This investigation will be wrong about something. All investigations that make specific predictions under genuine uncertainty are wrong about something. What I hope it gets right is the mechanism, the history, the physical stakes, and the honest assessment of where the evidence points. Those things don't become wrong when the outcome is known. They are the framework for understanding what happens, whatever happens. The aurora will be the visible signature of what happens. When the storm arrives, the charged particles funneled into the upper atmosphere along magnetic field lines will produce curtains of green, red, and purple light at altitudes of 100 to 300 kilometers. Oxygen atoms and nitrogen molecules excited by the electron cascade, radiating as they return to ground state. If you are in North America, Europe, or the Southern Hemisphere's equivalent latitudes, and the sky is clear, and you are away from city light, go outside. What you will see is the physical evidence of the magnetic reconnection happening above your head. It is genuinely beautiful. It is also the sky telling you, in the most vivid possible way, that the storm is real and that it is happening. But the aurora is not the investigation. The investigation is what happens to the infrastructure under the visible display. In the hours and days after the storm's main phase, the data that matters will come from several sources. Power utilities in the Northeast and Canada will report, through their regulatory filings and operational status updates, whether any equipment was damaged. The USG's observatories will publish their storm-time magnetic field records. The full-time series of the event, nanoteslas per minute, available for anyone to examine. The Space Weather Prediction Center will publish its post-storm analysis, including the measured DST minimum and the peak solar wind parameters as observed by DSCOVR and ACE. The satellite operators, SpaceX, government operators, commercial constellation managers will report anomalies and losses through their public communications. And then there is the question that this storm will not fully answer, regardless of its severity: whether the accumulation of storms in this solar cycle is driving a policy response adequate to the risk. The June 2024 G5 event produced significant public and political attention to space weather preparedness. The September 2024 active period produced another round of warnings. Now this event, Solar Cycle 25, is not finished. The cycle is near its peak, which means the next 12 to 18 months are the highest risk period for additional major events before activity begins to decline. Each event that occurs without catastrophic consequence carries two readings. Either the system is more resilient than worst-case models suggest, or we are accumulating near misses until the probability finally resolves against us. Daniel Baker, whose July 2012 analysis I cited earlier, has said publicly, and I think this is the plainest and most honest framing of the policy problem, that we are not a society that responds well to near misses. We respond to events. The Fukushima disaster changed nuclear safety regulation. Hurricane Katrina changed federal emergency management. The 1989 Quebec blackout produced some grid hardening measures. But the hardening in each case was proportional to the damage that actually occurred, not to the damage that the close call analysis said was possible. The July 2012 near miss produced a significant scientific response: papers, conferences, congressional testimony. It produced a policy response that engineers in the field have characterized as inadequate relative to the modeled risk. The event that is approaching Earth in the next 48 hours is not guaranteed to be the one that forces a reckoning. It may be severe and recoverable, confirming the first or second interpretation and producing another round of warnings that receive appropriate attention for a few weeks before receding from public consciousness. Or it may be the event that proves the third interpretation. Or, and this is the honest scientific possibility that I think gets the least airtime in the public conversation, it may be the dress rehearsal. The storm that causes significant but survivable disruption, demonstrating the specific failure modes at a scale that is large enough to be undeniable and small enough to be recovered from, and thereby creating the political and institutional will to do what the engineering community has been recommending for 2 decades. What NERC's geomagnetic disturbance standards require, what the independent engineering analyses recommend, and what the available technology could provide, if deployed, is a combination of GSE monitoring in real time at critical substations, GSE blocking devices on the most vulnerable transformers, and operational procedures that allow grid operators to take preemptive protective action before a major storm rather than scrambling in its final hour. None of these are exotic technologies. GIC blocking capacitors exist and have been installed in some substations. Real-time monitoring exists and has been expanded in some networks. The procedures exist on paper. The gap is implementation, specifically implementation of these measures at the large, custom, impossible to quickly replace transformers in the highest risk geographic zones. The cost of full implementation has been estimated at various figures across different analyses, from a few $100 million to a few billion, depending on the scope and the configuration of the measures. The cost of a worst-case grid failure in the Northeast, per the independent analyses I have cited in this investigation, is measured in trillions. The ratio is not subtle. But the investment in mitigation requires accepting that the catastrophic scenario is real, and that action against a probabilistic risk, even a large one, is justified. Societies are not naturally good at this, and governments are particularly not good at it, because the political reward for preventing a catastrophe that doesn't happen is much smaller than the political cost of spending money on it. This is where the investigation comes to rest. Not on a prediction about what will happen in the next 72 hours. That will be determined by physics, not by documentary scripts. But on the honest observation that what happens in the next 72 hours is one data point in an ongoing series. The sun will produce more events. Solar Cycle 25 is near its peak and will remain elevated for another 12 to 18 months before declining. The physical mechanisms, cannibal CME compression, GIC coupling into resistive ground, transformer thermal damage thresholds, do not change between now and the next event. We will be watching. The DSCOVR data stream is public. The USG's observatory data is public. The NOAA Space Weather Prediction Center forecast discussions, updated every few hours, are public. Everything you need to follow this event in real time is accessible to anyone with an internet connection and the inclination to look. The links to all of these data sources will be in the description, because this channel believes in giving you the tools to verify everything we say and everything we conclude.
When DSCOVR sees the shock, the clock starts. What the clock counts down to will tell us which interpretation was correct. We will be here for that. We will be here for the post-storm analysis. And we will be here for the next one. Because there will be a next one. The sun hasn't finished with this particular conversation yet.